Welcome to Lesson 6A, Other Normal Shock Relations. In this lesson, we'll apply equations from the previous lessons to generate equations for how other properties, like pressure, temperature, etc., change across a normal shock. I'll also discuss irreversible losses across a shock. Our goal is to get normal shock ratios for pressure, speed, etc. as functions of m1 and gamma only. From the previous lesson, we generated an equation for m2, the Mach number downstream of a shock, as a function of m1 and gamma, where we're assuming an ideal gas. Now let's look at equations for other properties, like temperature, pressure, etc., across the shock. Here's the equation we derived last time, and I'll start renumbering in this lesson, so I'll call this equation 1. To get the pressure ratio P2 over P1, we can use either the Fano equation or the Rayleigh equation. I'll choose the Rayleigh equation since it's simpler, and I rewrite it here, and I'll call this equation 2. Notice that this pressure ratio has both m1 and m2, but if we plug equation 1 into 2, we can eliminate m2 to get what we want, which is P2 over P1 as a function of m1 and gamma only. So let's plug 1 into 2. This involves some algebra, which I'm not going to show, but the final result is 2 gamma m1 squared minus gamma plus 1 over gamma plus 1, and I'll call this equation 3. And as a check, at our old friend m1 is 2.60 for air, we get a pressure ratio of 7.7200, which agrees with what we found in previous lessons at this Mach number and gamma. This equation is easier to use because we don't have the intermediate step of finding m2. We can do the same thing for T2 over T1. Recall that T2 over T1 was given by this expression, which I'll call equation 4, and it also involves calculating m2 as an intermediate step in order to get the temperature ratio. If we plug equation 1 into equation 4, we can get T2 over T1 as a function of m1 and gamma only. The algebra is rather involved to do this, and in most cases I prefer to use this equation rather than the one we derived from here.
Are you going to show us that equation?
No, BJ, I'm going to leave that one for homework, but keep in mind that you don't really need it. You can always calculate m2 from equation 1 and then use equation 4 to get T2 over T1.
Okay, I just thought I'd ask.
It never hurts to ask. I'll just say try this on your own and leave it at that. Now let's consider the density ratio. Using the ideal gas law, we have P2 over RT2 divided by P1 over RT1. The R's cancel, of course, and we can write this as P2 over P1 divided by T2 over T1. Again, there's lots of algebra here, which I'm going to leave out, and you can get rho 2 over rho 1 is gamma plus 1 m1 squared over 2 plus gamma minus 1 m1 squared. I'll call this density ratio across a shock as equation 5. Now consider the speed ratio, V2 over V1. Well, recall conservation of mass for this steady one-dimensional problem is rho 1 V1 is rho 2 V2 across the shock, from which V2 over V1 is simply rho 1 over rho 2. So we can get V2 over V1 as simply the reciprocal of this equation 5, and I'll call this equation 6, but it's usually easier just to calculate rho 2 over rho 1 and just take 1 over that to get the speed ratio. Now let's consider stagnation properties. Recall that the flow across a shock is approximated as adiabatic and one-dimensional, and we know that T02 is equal to T01. That's our energy equation, and I'll call that equation 7. So we already know that stagnation temperature is constant across a shock. What about stagnation pressure? Well, again, as I've said many times, you think about this in terms of ratios. So P02 over P01 is P02 over P2, P2 over P1, and P1 over P01. Since the flow is approximated as isentropic on either side of the shock, we can use the isentropic equations for these two ratios, and for this term we have a choice. We can use the Fano equation, or the Rayleigh equation, or equation 1, whichever one we choose. I'll use Fano. Let's write out these equations. We have 1 plus gamma minus 1 over 2 m2 squared, gamma over gamma minus 1. And here we have the same thing, except with a negative exponent, since it's the reciprocal of this, and it's for m1 instead of m2. And the Fano equation is written out here. And the reason I chose Fano was that this grouping of terms is the same as this, and this grouping is the same as this. So when we multiply these together, we can combine the exponents. Namely, p02 over p01 is 1 plus gamma minus 1 over 2m2 squared over 1 plus gamma minus 1 over 2m1 squared to the gamma over gamma minus 1, combining these two terms, and then rewriting this with an exponent of negative 1/2 times m1 over m2. And since these are the same, we can combine these exponents. Gamma over gamma minus 1 minus 1/2 can be simplified to gamma plus 1 over 2 gamma minus 1. So p02 over p01 is m1 over m2 times our expression in square brackets to the exponent gamma plus 1 over 2 gamma minus 1. This I'll call equation 8, which is a nice simple result, although it contains both m1 and m2. If we also apply equation 1, our equation for m2 as a function of m1, and after some algebra which I won't show, we get the following equation for p02 over p01 as a function of only m1 and gamma, and I'll call that equation 9. Again, I'll check these equations at m1 equal 2.60 and gamma equal 1.40. Both of these give 0.46012. Notice that for this case, p02 is less than half of p01. In other words, p02 goes down across a shock. I'll discuss this in a little more detail in a minute. Let's do a qualitative summary across a normal shock. First, some properties that stay the same. In other words, they do not change from 1 to 2 across the shock. Well, we know that m.2 equal m.1 by conservation of mass. We also know that stagnation enthalpy does not change by conservation of energy. And for an ideal gas, stagnation temperatures also do not change. And we said in a previous lesson that the sonic speed of sound, A star, also does not change across a shock. Properties that increase across a shock are density, temperature, pressure, specific entropy, or if you use uppercase S is the actual entropy. From this we also know that A2 is greater than A1 and H2 is greater than H1, since A is square root of gamma RT and H is CPT. Also, it turns out that A star 2 is greater than A star 1. As we discussed in our lesson about supersonic wind tunnels, if we have a converging diverging nozzle with a shock and area A star 1 at the throat, in order to bring this back to sonic conditions, we'd have to have a second throat with A star 2, but as drawn, A star 2 must be bigger than A star 1. In other words, the flow will choke at a larger throat area than initially, with flow being from left to right, of course. Finally, consider properties that decrease across a shock. We know that Mach number must go from supersonic to subsonic, so m2 is less than m1. Speed v2 is also less than speed v1. This is a direct result. Since density increases across a shock, speed must decrease, since ρ1 v1 is equal to ρ2 v2. They're inversely related. As I showed in our example at Mach number 2.6, p02 is less than p01, and it turns out that ρ02 is also less than ρ01. I want to briefly mention this loss of stagnation pressure. We have p01 in the upstream tank in this duct, and that remains all the way up to the shock, since the flow from here to here is approximated as isentropic. But p0 drops significantly across the shock, and from here on, P0 is P0 too. Thus we have a loss of stagnation pressure, which is what drives the flow. This loss is due to irreversible losses and an increase in entropy across the shock. We've lost some what I call oomph to drive the flow. If you ignore everything upstream of the shock and start with the stagnation pressure P0 too, you have much less oomph to generate this flow for a given back pressure, since it's the ratio of P0 and Pb that determines this flow. Here I summarize all the equations for a stationary normal shock in an ideal gas. These are the static properties, Mach number, characteristic Mach number, static pressure ratio, static temperature ratio, static density ratio, and speed ratio. And these are the stagnation properties, H0, T0, and the ratio of stagnation pressures, P02 over P01, where I've used the equation that is in terms only of gamma and M1. Let's calculate these at our test case of M1 equal 2.60 and gamma equal 1.40. Plugging into these equations, we get M2 is 0.50387, P2 over P1 is 7.7200, T2 over T1 is 2.2383, rho 2 over rho 1, or V1 over V2, turns out to be 3.4490, and I'll comment, notice how much rho increases across a shock, almost a factor of 3.5 at our test case Mach number. And finally, the stagnation pressure ratio, as I've already mentioned, is 0.46012. Let's compare these results to those of the compressible aerodynamics calculator. Here's the online compressible aerodynamics calculator for the normal shock case with the default of 1.4 and a Mach number 1 of 2.60. We calculate M2 0.50387, P2 over P1 7.72, rho 2 over rho 1 is 3.4490, temperature ratio is 2.2383, and P02 over P01 is 0.46012. There's also a P1 over P02, which will become useful later on. As you can see, the online calculator values agree with our calculations, which should make you happy.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.